Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this lecture, we're going to look at the role of alcohols in the formation of esters and inorganic esters. Esterification is the reaction of an alcohol with an acid or acid derivative to give an ester. Now, we're only going to touch on ester formation, but you should not think it's not important. In fact, we're going to be revisiting it in second semester. And esters are a very important class of organic compound. The reaction we're going to present is a simplification of the whole area of ester chemistry. And we're actually going to consider it separately when we get to carboxylic acid derivatives. Now, esters form by the reaction of a carboxylic acid and an alcohol. So here I'm reacting it with ethanoic acid, a carboxylic acid, and we're going to react that with the alcohol, 1-propanol. This is an equilibrium reaction usually carried out in the presence of acid. Yields are not high because it is an equilibrium, and you will actually produce the ester. You also produce water. We can increase yields by removing the water and shifting the equilibrium to the right. So ethanoic acid plus propanol will produce propyl ethanoate. There's a space between the name ethanoate and propyl. Its common name is N-propyl. Acetate. Now, what's interesting is we can create a class of ester by reacting alcohol with various inorganic acids. These are called inorganic esters. And effectively what we're doing is we're replacing the carbon of the C double bond O with an inorganic sulfur or nitrogen. The first inorganic ester we want to look at are the inorganic esters called nitrates. Nitrates can be formed by taking molecule like methanol and reacting it with nitric acid. Nitric acid, HNO3, is better written as HONO2 because the hydrogen is really bound to an oxygen. It is a fairly powerful acid. So nitrates are esters of nitric acid. HNO3. If we take nitric acid and react it with methanol, we will produce water and methyl nitrate. Do not get this confused with the molecule CH3NO2. CH3NO2 is nitromethane. In the case of nitromethane, carbon is bound to nitrogen. But methyl nitrate, carbon is bound to an oxygen. So they are different molecules. Now, in order to properly understand the reaction mechanism, we need to understand the structure of nitric acid. And so it behooves us to draw the Lewis structure for nitric acid. If I am going to draw the Lewis structure for this molecule HONO2, I need to know the total number of valence electrons. Total number of valence electrons, 3 oxygens, 18, plus 5s, 23, plus 1 for hydrogen, we have 24 electrons. Nitrogen has 5. Oxygen has 6. Hydrogen has 1. Oxygen has 6. And oxygen has 6. And so I can start joining to try and get 8 electrons around every atom. If I do this, I get 8 electrons around this oxygen. I can start sharing. Two, 4, 6, 8. Nitrogen's happy. Join these 2 up and dump them in a dative bond. That will give me 8 electrons. Let's draw it over here. And there you have the Lewis structure for nitric acid. The nitrogen, if I do the formal charge, is positive, and this oxygen is negative. All right. Given now that we have the Lewis structure for nitric acid, we can begin to consider several possible reaction mechanisms. So, if we want to understand how this reaction actually proceeds, we can make several mechanistic proposals. The first mechanistic proposal is based on the presence and use of a very powerful acid. We know methanol requires acid to produce a good leaving group. So, in the presence of a powerful acid, some of the methanol will get protonated and become the protonated alcohol, or oxonium ion. So, step 1 of our proposed mechanism is protonation. So protonation. Step 2, nucleophilic attack. Via SN2. If we have H plus protonating the alcohol, that means nitric acid is given up an H plus. That means there is some nitrate ion floating around, NO3 minus. Perhaps NO3 minus can act as a nucleophile and do a backside attack on carbon. Now that carbon has the good leaving group, water, which is a weak base. So, there you go, SN2. Well, this represents just one mechanistic proposal. There are other possibilities. This next mechanistic proposal is really based on the type of chemistry we're familiar with, water. If we take two water molecules, we know water can react with itself. To produce equal amounts of H3O plus and hydroxide. We've seen this before. No surprises there. This is known as the kW of water. At pH of 7, the concentration of H3O plus and hydroxide is equal and is 1 times 10 to the minus 7 moles per liter. Now, what's interesting about this is we can do the same sort of thing with nitric acid. I can take one nitric acid reacted with another and produce, via equilibrium, NO3 minus and a protonated nitric acid. Now I grant you, concentrations of this will not be great, just like the water scenario. But once we protonate the nitric acid, this unit can readily fall apart to H2O plus NO2 positive. NO2 positive is called nitronium ion, and you are responsible for that name. Nitronium ion. Now it's very important that we understand the structure of nitronium ion because the next step of our mechanistic proposal involves it. So let's draw the Lewis structure for nitronium ion, and I'll see if I can do it up here. NO2 plus. How many valence electrons? 6 times 2 is 12, plus 5 is 17, minus 1 for the positive charge, 16 electrons. Oxygen has 1, 2, 3, 4, 5, 6. Nitrogen has 5, 1, 2, 3, 4, 5. Oxygen has 6. 1, 2, 3, 4, 6. Subtract 1 for the positive charge, and we're left with this. Which gives me this. 8 electrons around every atom. And a positive charge on nitrogen. Alright, so this is the NO2 plus. Now what we notice is nitrogen has 2 electronegative atoms on it. And it has a formal positive charge. Nitrogen's electronegative, so it prefers having electrons, plus with 2 electronegative oxygens and the positive charge, nitrogen becomes a very powerful electrophile. It is desperate for electrons. And we have a lot of electron density available in the form of methanol. Methanol is a weak nucleophile, but in the presence of something that is so electron-seeking, the lone pairs available on oxygen represent an electron-rich target. So if this guy reacts with NO2+, effectively what can happen is the N plus grabs 2 electrons from the lone pair, making the methanol act as a nucleophile, and the oxygen pi electrons move out to create a lone pair, and I get methyl. Nitrate. Now this intermediate has 2 adjacent positive charges, so you know it's not going to positive charge on nitrogen, positive charge on oxygen. This is not going to last very quickly and very long. It's not going to last for very long. And very quickly, we're going to deprotonate this. And get our methyl nitrate. So the intermediate loses a proton. We produce a methyl nitrate, our CH3, CH3O and 2. Okay, so that's what that molecule is. Now, what's interesting about all of this, these represent 2 independent mechanistic proposals. I could have written down step titles for the second mechanistic proposal. The first step would have been production or preparation of nitronium ion. Step 1, formation of nitronium ion. So if I wanted to, I could have called this step 1. And I could have called it formation. Of nitronium ion. And step 2 would have been nucleophilic attack, but not SN2. Okay, I would have just titled it nucleophilic attack by methanol. Okay, nucleophilic attack of methanol on NO2+. This nucleophilic attack, maybe I've got room to write it. So if I went this way. So step 2. You might think, well, this is just the same as the previous. The first step's a little different, but both second steps involve nucleophilic attack. But if you look carefully, you'll notice that the two mechanisms are quite different. In step 2 of the first mechanism, your nucleophile is nitrate, NO3-. But in step 2 of the second mechanistic proposal, the nucleophilic attack is methanol. No, we can conclude that these are two very different mechanisms. Now, we can never prove a mechanism correct, but what we can do is prove a mechanism wrong. Up to now, we've never used the tool of isotopic labeling to distinguish between mechanisms, and I would like to show you how this works now. There is an isotope of oxygen called oxygen 18. Most oxygen is oxygen 16. That is, it has 8 protons and 8 neutrons. But this rarer isotope called oxygen 18 has 8 protons and 10 neutrons. It also has a nuclear spin. Oxygen 18, because of its nuclear spin, gives a signal, an NMR spectroscopy. And different molecules give different signals, and they can be distinguished by nuclear magnetic resonance spectroscopy. So suppose we bought methanol that was labeled with oxygen 18. That is, the oxygen 18 in the methanol molecule has been enriched, perhaps 99% oxygen 18. Because it gives a signal, we could detect the oxygen 18 in the methanol. We could also, and I'm using asterisks to indicate the oxygen 18, track where it went. So when nitrate attacks and water leaves, the oxygen 18 in this mechanism ends up in water. Well, where would the oxygen 18 in the methanol end up in the second mechanistic proposal? Well, it'd end up here. It ends up in the methyl nitrate. This is oxygen 18. Now, the oxygen 18 signal for water is different than the oxygen 18 signal for methyl nitrate. So we can do an experimental test and simply ask the question, where does the oxygen 18 end up? If the oxygen 18 ended up 50% in the methyl nitrate, 50% in the water, it would be possible that we have two mechanisms taking place at the same time. However, this is fairly rare. Usually one mechanism predominates because it's more energetically favorable. If we carry out this experiment and we observe the oxygen 18 signal, we find out 100% of the oxygen 18 is in the methyl nitrate. That means the top mechanistic proposal is wrong, because none of the oxygen 18 ended up in water. Now, we could have made an intuitive guess, or we could have concluded that the top mechanistic proposal was unlikely. And that is because of our knowledge of nitric acid. Nitric acid is a powerful acid. Hence, NO3- is a very weak nucleophile. Even with a good leaving group, nitrate is unlikely to act as a nucleophile attacking protonated methanol. However, the formation of the nitronium ion is an extremely favorable reaction. There will be certain concentrations of nitronium. And as I've stated earlier, nitrogen does not like the positive charge. It's an electronegative atom with 2 electronegative oxygens, and nitronium ion is a very powerful electrophile. It wants electrons. So the attack of methanol on the nitronium ion is fairly reasonable. Well, there you have it. The use of isotopic labeling can be advantageous in distinguishing which mechanism is incorrect. Now, remember, this does not prove the bottom mechanism is the correct mechanism. It could be wrong as well. However, it could just be coincidentally putting in the oxygen 18 and methyl nitrate, which is experimentally observed. The actual mechanism may be some yet undiscovered mechanism we have not thought of or proposed. So just because the experiment supports the mechanism doesn't mean it proves it. All right. Now, nitrates are very important. Molecules like methyl nitrates are known vasodilators and can be used in the treatment of angina attacks. And nitrates are also important because of molecules like this. We can take a molecule (1,2,3) propane-triol, or glycerol as it is commonly known, react it with nitric acid. In fact, let's react it with 3 nitric acids. And this will produce this molecule. This molecule has a common name of nitroglycerin. You may have heard of it. Nitroglycerin is that viscous liquid which, if you just shake slightly, it explodes. Nitroglycerin and organic nitrates are explosive compounds. The reason is, unlike simple combustion processes where intermolecular collision with oxygen is required and you must wait around for the oxygen to collide with the carbon, this molecule is ready to undergo a molecular rearrangement to CO2. In other words, the oxygen is already attached to the molecule. You do not have to wait for intermolecular collision. And thus you have an explosive. Rearrangement occurs much faster, releasing lots of energy in the production of CO2, which transfers to other molecules. The reaction is very rapid and very exothermic, resulting in an explosion. Now, in the early days of mining, nitroglycerin is used to move rocks out of the way and crack open the earth so we can access precious metals. However, there were many losses of life with people transporting and moving this viscous liquid. Alfred Nobel learned that you could stabilize nitroglycerin by pouring it on wood chips or cellulose. Cellulose, when it absorbs the nitroglycerin, would interfere with the transfer of energy, thereby stabilizing it somewhat. He produced dynamite. Now, his goal was to save lives in the mining industry, and indeed that is what happened. But of course, the military very quickly got a hold of his invention, and loss of life was occurring because of military use of dynamite. Because of this, he founded the Nobel Peace Prize in order to encourage the peaceful development and usage of dynamite. It was a prize to encourage people to come up with ideas for a way of using this material in a peaceful means. Now, nitrate compounds are used as high explosives even today. And they're used in Alberta and Fort McMurray to expose the tar sand which is under overburden, or rock. The dirt and rock could be blasted to expose tar sand, and likewise the tar sand can be reacted, or explosions can be made to occur in the tar sand to make the tar sand easier to remove and dig up. All right. This molecule, as I said, is nitroglycerin. Okay. Let's move on. Let's look at the inorganic ester referred to as sulfates. These are esters of sulfuric acid. Now, sulfuric acid can be reacted with methanol much the same way that we reacted nitric acid. I am not going to look at the mechanism of this reaction. We've already seen the formation of one inorganic ester. But suffice to say, sulfuric acid proceeds the same way nitric acid does. Two sulfuric acids can react, and if you do that, you can produce the electrophile SO3 gas. Methanol can attack SO3 gas and produce the inorganic esters. If methanol reacts with sulfuric acid, we can produce CH3OS. This is referred to as methyl hydrogen sulfate. Methyl hydrogen sulfate. If I repeat the reaction and use two methanols, on attacking sulfuric acid, I can produce dimethyl sulfate. So there you have it. Okay. You're responsible for the naming of the products. Now the problem with this reaction is this group. And of course this group. Are good leaving groups. Why are they good leaving groups? Well, if you think about it, H2SO4 is a very powerful acid. Lose a proton, you have HSO4-, which is a weak base. If I was to attack the methyl and kick this group out, that would be HSO4-. HSO4-, because it's such a weak base, is an excellent leaving group. Likewise, this group would be an excellent leaving group. Which means these guys are susceptible to nucleophilic attack. So typically, this reaction is conducted at low temperatures, around 0 degrees Celsius, to inhibit nucleophilic attack. So if you want to isolate these, you carry out the reaction at low temperature. Suppose I have a primary alcohol, like methanol. If I react it with H2SO4, at 0 degrees C, I will produce either the ethyl hydrogen sulfate or the diethyl sulfate derivative. I'll write that one up here. If I have room. And I'm going to run out of room. So, I either get that or the diethyl sulfate, depending on the number of equivalents. So let's just leave it as ethyl hydrogen sulfate. If, however, I use H2SO4, at 140 degrees C, I will get the ethanol attacking this molecule. It will actually do an SN2. The ethanol will come in, backside attacking, will kick out HSO4-. That'll make a protonated ether, which loses proton, and will give me diethyl ether. That is, if this guy came up here and attacked that carbon, this guy would leave. And then you'd have ethyl O ethyl with an H off of it. That would be a proton, and you deprotonate that, you'd get diethyl ether. If you raise temperature even higher, say to in excess of 180 degrees, say like, well, let's just put 180 degrees. Then the ethanol won't nucleophilically attack, but rather it'll act as a base and grab a proton off the CH3. This group will leave. You'll get anti-elimination, and you'll produce ethene. So this guy goes E2. This is SN2. And this is just ethanol attacking the sulfur. So you need higher energy. And so we conduct or produce these esters at low temperature to avoid SN2 and E2 reactions. How about trying to give me a name for this molecule? What'd you get? Phenyl, hydrogen, sulfate. Very good. Phenyl hydrogen sulfate. You react phenyl hydrogen sulfate, or you produce phenyl hydrogen sulfate by the reaction of phenol with sulfuric acid. But phenyl hydrogen sulfate is not this molecule. And students often mix up these two names. These two molecules are different. Notice the phenyl in the top molecule is attached to oxygen and not the sulfur. In the bottom molecule, the phenyl is attached to sulfur. This bottom molecule is called Benzenesulfonic acid. Now, benzenesulfonic acid is a powerful acid like sulfuric acid. It is powerful because once it deprotonates, if you take the H plus off, and for the phenyl, I'm going to just use R, you get R, S, double bond O, double bond O, it's resonance stabilized. R is my phenyl group. as you can see, the negative charge moves out around the oxygens. Because of this, the negative charge is spread out over all three oxygens and is heavily stabilized. Stabilizing the negative charge favors loss of H+ and makes this derivative a very good acid. Also, the minus group, the RSO3-, would be a good leaving group. If sulfonic acid's a good acid, that makes this material a weak base, and hence a reasonable leaving group. A related acid to benzenesulfonic acid is this acid, referred to as p-Toluenesulfonic acid. Now, these reagents are useful because the inorganic esters we make can be used to retain, if you like, chirality molecules. And I'll give you an example. Suppose I had the following alcohol. Let's make that a little better. There we go. Suppose I have this alcohol. This is sec-butyl alcohol, a 2-butanol. If I check the priority, 1, 2, 3, 1, 2, 3, it's counterclockwise. So this is S-butan-2-ol. If I have a pure enantiomer of an alcohol, it probably costs a fair amount of money to get it chirally pure. If I want to react it and, say, make the iodo derivative, I probably wouldn't want to use HI because HI would take a secondary alcohol, favor SN1, and it would give me a racemate. I'd lose my chirality because SN1 gives you a racemic mixture. It'd be nice if we could find some way of reacting this material and still retain chirality. Well, what we can do is we can take p-Toluenesulfonic acid we can react it with SOCl2. Now SOCl2 we've already seen in alcohols, and SOCl2 chlorinates alcohols or replaces OH groups with chlorine. We can do it in ether or amine solvent and have different chiral effects happen. But SOCl2 replaces OH groups with chlorine, so p-Toluenesulfonic acid would react to make what we call p-Toluenesulfonyl chloride. This material is called p-Toluenesulfonyl chloride. It's also called, common name is Tosyl chloride. Now, Tosyl chloride is a very useful reagent. When you react with alcohol with Tosyl chloride, you can make an inorganic ester. You can make what is called a sulfonate. If you take Benzenesulfonic acid and deprotonate it, you get Benzenesulfonate. If you take p-Toluenesulfonic acid and deprotonate it, you get p-Toluenesulfonate. Let's take a look at this. What happens if I take this and I react the two? Well, sulfur has two electronegative oxygens, electronegative chlorine. There's quite a delta plus on sulfur. And so the sulfur gets attacked. This is push pi electrons out. So, the molecule we get will look something like this. Now this intermediate quickly reforms its double bond and chloride will leave. So we've lost Cl minus here. Okay, now I'm going to combine two steps here. If you look at this right here, because I'm running out of room, this H plus would be lost in a deprotonation step. So I'm going to put minus H plus as well and take that H plus away. So that comes off, making a lone pair here and getting rid of the positive charge. What have we got? Well, in place of the H in p-Toluenesulfonic acid, we now have this alkyl. This is named as an inorganic ester. I still retain 1, 2, 3, it's still S, okay? So it's an S2-butyl or an S-sec-butyl. Let's call it S-sec-butyl space p-Toluenesulfonate. Drop, when you're naming esters, you drop the ic acid and you add A. All one word. Sulfonate and toluene's all one word. The common name would be S-sec-butyl. And then a space. And it's a tosylate. So, here are some names. So either S-sec-butyl space p-Toluenesulfonate or S-sec-butyl tosylate. Now if that methyl wasn't here, this would be an S-sec-butyl benzenesulfonate from Benzenesulfonic acid. So this methyl is what makes it a p-Toluenesulfonate. Well, what's so special about this reaction? Look at the product and look at the starting material. The chiral carbon is unchanged and unaffected. Okay, why? Well, the reaction took place through the oxygen, not the chiral carbon. The oxygen attacks the sulfur. The chiral carbon is never attacked. All right? What good is this S-sec-butyl p-Toluenesulfonate? Well, it turns out that this group is such a good leaving group because it's such a weak base that you now can do a reaction on this material. What reaction? Well, let's clear this off. I can take this material with any nucleophile, and because it's such a good leaving group, my secondary no longer goes SN1. But with strong nucleophiles, the secondary will do an SN2. Okay, so what? Well, the reason this is important is I can retain chirality. See, if you go SN1, your S would have become a racemic mixture. And sometimes that's not desirable. Sometimes what you desire is to carry out a reaction where you get inversion of chirality. So say I hit this guy with a powerful nucleophile like cyanide. He will go SN2 and he will produce the p-Toluenesulfonate anion as my leaving group because it's a good leaving group. So this is p-Toluenesulfonate, all one word. Sometimes common name is tosylate. And the p-Toluenesulfonate or tosylate anion, after it leaves, the cyanide comes in and does backside attack. SN2. So you get inversion. Okay, I get inversion. So let's draw CH3 here, CH2. Carbon, H, methyl, and I get a C triple bond N. Now you haven't learned how to name nitriles yet, and there's no problem. You don't need to name it at this point. We'll be covering that later. But if I prioritize, this carbon as a nitrogen, he's 1, he's 2, he's 3. This is R, 2-methyl butane nitrile. Now you do not need to know that name. But what's neat about this reaction is this was such a good leaving group, we got an SN2. I could have used I-. I could have used I- and made R 2-iodobutane. If, however, on the original starting material I'd used HI instead, I would have done SN1 and got a racemic mixture. So this methodology, putting the good leaving group on the molecule, allowed me to do SN2 and retain a chirally pure enantiomer. So sometimes it's advantageous to create really good leaving groups. Now, as I said, this deprotonated p-Toluenesulfonic acid is called p-Toluenesulfonate or tosylate. If, however, I had not had the methyl, if there was no methyl here, then this would have been Benzenesulfonyl chloride. And that is also the common name. Benzenesulfonyl chloride. This would have been a benzenesulfonate, so this would have been S2-butyl or S-sec-butyl. Named like an ester. The alkyl attached to the oxygen is a separate word. S-sec-butyl benzene sulfonate. Didn't quite get the sulfonate on the screen. And this guy is just a benzenesulfonate. It's the anion. So you're responsible for all these names and responsible for understanding A, why benzenesulfonic acid and p-Toluenesulfonic acid are strong acids because of the resonance in the anion, and it stabilizes the anion and makes it form faster by losing H+. Why they are weak bases and good leaving groups, because benzenesulfonic acid and p-Toluenesulfonic acid are so strong acids. How to prepare benzenesulfonyl chloride and how it can be used to make alkyl benzenesulfonates and alkyl p-Toluenesulfonates, and the usefulness in promoting SN2 reactions that retain a chiral center. they actually give you inversion. Notice you should also be able to indicate why the chirality was not affected when you reacted with benzenesulfonyl chloride or p-Toluenesulfonic chloride. And that was because the alcohol reacts through the oxygen. Well, there you have it. A series of inorganic esters. We have nitrates, sulfates, and sulfonates. Be careful not to confuse the sulfonate esters with the sulfate esters. Watch your nomenclature. Don't confuse phenyl hydrogen sulfate with benzenesulfonic acid. That's a very common question. Okay, the last section of material we want to look at deals with the oxidation of alcohols. Alcohols can be oxidized. Alcohols can be oxidized. Let's begin with primary alcohols. Alcohols such as N-butyl alcohol or 1-butanol. We can hit this molecule with an oxidizing agent. O in square brackets simply means oxidizing agent. And if we do, we'll go through to butanoic acid. Now, what are some oxidizing agents that can do this type of reaction? Well, we could use, for example, KMnO4 in acid. We could use C chromium oxide, CrO3, in acid. We can use an acid form of the chromium oxide, and it's called chromic acid, H2, having difficulty, CrO4, where the acid is actually built into the molecule itself. We could use sodium dichromate, Na2Cr2O7 in acid. Now the acid could be things like sulfuric, acetic, there's various acids you can use. So there are many possible oxidizing agents that can be used in this reaction. Any one of these would work. The reaction actually goes through the aldehyde. The aldehyde is actually formed during this transition to carboxylic acid. The interesting point is that the aldehyde is very difficult to isolate. You can't stop the reaction at the aldehyde. Now, because the starting material, the alcohol, and the carboxylic acid both have hydrogen bonding, it would be possible to set up a reaction vessel that is above the boiling point of the aldehyde, but below the boiling points of either the alcohol or carboxylic acid. This would allow you to distill off some of the aldehyde as it forms. But you can expect the yields to be low, because not all of the aldehyde would escape. it is possible to stop the reaction at the aldehyde if you poison the chromium oxide catalyst. If you use CrO3.2py, the solvent is CH2Cl2. We can use different solvents. This is just the solvent. It doesn't participate in the reaction. Okay, so the reagent CrO3.2py, and we can get just the aldehyde. Now CrO3.2py, py stands for pyridine. Pyridine is a benzene ring that has a nitrogen in place of a carbon. The nitrogen atom binds to the chromium. Effectively, the pyridines block the attack of the aldehyde by the oxidizing agent. That is, it allows the alcohol to interact to produce the aldehyde, but prevents further attack, and you get only the aldehyde. The pyridine, py stands for pyridine, binds to the chromium. So, sometimes I'll give a solvent under the arrow, sometimes there will be no solvent. So whether you see a solvent or with CrO3.2py or just CrO3.2py, you know you're going to get only the aldehyde. Okay, what about secondary alcohols? What if you take, not own, writing the product. What if you take sec-butyl alcohol or 2-butanol? Well, as you just noticed, I started to draw the product. With any of those oxidizing agents, those powerful ones, we get the ketone. So secondary alcohols give ketones, whereas primary alcohols give carboxylic acids. And so we get 2-butanol. What if I use a tertiary alcohol? A tertiary alcohol with oxidizing agent. Well, you do not get a ketone because that would create five bonds to carbon. I can't draw this. This can't form. That would be too many bonds to carbon. So in the presence of oxidizing agent, like CrO3 and acid at room temperature, I get no reaction. But what if I tried to force it? What if I applied oxidizing agent and heat? I tried to push the reaction. Well, because oxidizing agent is in the presence of acid, acid would protonate the alcohol. In the presence of heat, tertiary alcohols do E1. I would get an alkene as an intermediate. I would get this alkene. And then the alkene would go on to react with the oxidizing agent. Since we haven't covered alkene chemistry, we haven't determined what that would form. Suffice to say, it would split the double bond in two. And we'll look at how and what that forms later on in the course. Well, there you have it. We've covered the esterification reaction, inorganic esters, and the oxidation of alcohols. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.